things, and then I'm still going to record it and put it on YouTube, so in case you miss anything.
There will not be a YouTube live then, or there is a YouTube live?
Yeah, it's not going to be live on YouTube. It's just going to be live through Discord. So it should you should be able to double click on my name now, I think, and it should bring up my screen. Hopefully. And then my intention for the new rooms is basically so that when I ask you a question that I'm looking for you to respond to, what I would like to have you do is basically disperse to your rows. You're welcome to mix it up now that we don't have physical row assignments, but basically, like, when I ask this first question on the notes here, I would like you to sort of disperse to your rooms, talk about it for like a minute. I'll come in and sort of chat with each of you to hear what you're thinking, and then we can come back as a class and sort of have someone give each group's response, so that we get a little more discussion going amongst you instead of me just asking and then like waiting in dead silence for someone to respond. It's a little harder to get like those cues of when someone's going to talk on Discord. So let's try that today and see how that works. I thought it'd be a nice use of the features on Discord here if we can sort of move between one room and another to sort of have these small group discussions. So when I tell you to disperse, let's try that out, and then we'll come back to here. So okay, so hopefully everyone found the reading quiz and everything. I will also get out homework 6 and 8. It's going to be one homework, but it'll be covering both chapters that we didn't cover yet. I think 12-week grades are pushed back until the 14th of April, I think now. So we'll have our exam sometime the week of the 6th through the 10th. It'll be, it'll be a little slightly a different format because of the fact that, like, I'm going to basically assume that you're open everything for the exam. So it'll be a little more, analysis based, thinking about problem solving. Like if I give you a scenario, it'll be more of the scenario questions, basically. Just I'll tell you, like, given these parameters, what would you want to do, or what should you do in this case? So that'll be a bit more of what the exam is like this time, just because of the fact that I'm going to assume that you can like look things up online, and that you should look things up online. So just to sort of give you a heads up that will be a little bit different than it was last time. So otherwise, let's get started for today. So today we're going to be talking about contiguous memory allocation. So we sort of finished up with the intro to memory management last time. Today we're going to be going through some memory allocation techniques and eventually getting into paging. So in contiguous memory allocation, we're just essentially taking all of physical memory, and we are allocating some of that physical memory to each process. So if we have 4 gigabytes of memory, we're just basically splitting up a gigabyte here, a couple megabytes there, whatever each process is requesting to be able to run. We are going to allocate that amount of memory to that process. We're assuming that we don't sort of allocate them into fixed size chunks, because if we allocate fixed size chunks, some processes are only going to use a very small amount of memory. Some of them might use a very large amount of memory. We want to make sure that we can allow them to sort of specify how much memory they want to use and map them to an appropriately sized region of memory. So we have sort of setup that's right here, which is that we have low memory and high memory. We have the OS residing somewhere in that memory, and then we map processes into that memory as they execute. So at the beginning, maybe we have process 2, 8, and 5. When process 8 finishes, it can map process 9 into the space that was being used by process 8. So first question to disperse and talk about is, what should the OS do if a process needs more memory than is available in one of the holes that is present? So go ahead and disperse to the row channels and chat about it. Okay, Becker, what do we think?
I'm not sure I can hear Ryan at all, but
Oh,
or he hasn't been talking, which is also possible.
I can hear some clipping sound on his mic, but I can't hear his voice.
Me either.
Okay, so what do you think?
Okay, I moved to my
So I
laptop.
think they would need to restructure the way they've assigned the other processes, maybe, or do they just put it in a queue and wait until more memory is available? That seems really inefficient, though.
Yeah, I think those are both
in the-
reasonable responses, right? Yeah, so we could say queue it up and wait until wait until there is a free space available, or yeah, try to compact them so that we maybe move these around. If we need in the case that we have that last spot where we have process 9 and process 2 left, we could try to move them together, compress them to the top of memory, so that there's a little more space for something else. Cool.
The reading talked about like first fit, best fit, worst fit.
Yeah.
Too.
Yeah, so we will get to those, but yeah, compaction's sort of a one answer.
Okay.
So okay, I'm gonna move on to the next room. Okay, middle row. What do we got?
We were just saying you either just like put it in a wait queue, or you just throw an error at it.
Yeah.
So there's not enough space.
Yeah, that's reasonable. Yeah, so you might make it stall until there's enough space available somewhere. So cool.
Yep.
Okay.
Pretty much.
Okay, front row. What do we got?
So
You
we
can
we were just gonna put it into a wait or ready queue until there's enough space available.
Yeah. Sounds good.
Is that the? I was also going to say you could assign like multiple smaller open sections to a single process.
So we will get to that. Right now, we're talking about like each process is contiguous in memory, so we don't have that abstraction yet. But yeah, when we get to paging, that's sort of the ultimate solution is that we can, map it in a different way. But for now, yeah, that would be what we'd do. So we could put in a wait queue. So yeah, good answers. I'm gonna move you guys back to lecture, and then we'll continue on from there. Okay, great. So good answers all around. So I think we mostly got that we could put it in a queue, right? So we can put the process in a wait queue. I think Emily had another response that was pretty good. If you want to give it to the class.
Oh, wait. Yeah, you could try and reassign the processes that are currently in there, reallocate them in the memory, like combine processes 9 and 2, put them a little closer together so you have more space.
Yeah. Yeah, so we could try to compact the processes, put them, together in memory. So in this last case here where we have the OS process 9 and process 2, we could maybe say, put process 9 at the very top of memory, put process 2 next to process 9, and then we have a much larger hole to allocate into. So great, yeah, great responses. I think that worked pretty well. Seemed to get some good interaction there. So the OS can map processes into these holes in memory using a number of different strategies. So does anyone remember what the one that is that we just sort of find the first hole that's large enough? What's that called?
First fit?
First fit, yeah. So first fit is sort of the most efficient one, right? Because we just have a queue of open holes in memory. We look through that queue, or we have a list, right? And so we just look through that list, we find the first open hole, and then we... Oh, my stream is not up. Interesting. I don't know why that turned off. Okay, it should be back up. Sorry about that. I wonder if that happens when I switch rooms. Actually, that might be a problem.
Yeah, the Google Doc also updates just on the shared document you put in the general chat.
Oh, okay, yeah. Yeah, so I think in terms of, me giving out answers, you probably need to look at this one, and then if you have your own, like, local copy, you can, follow along with that as well. So yeah, so first fit's going to be the most efficient in terms of finding an open space. It's still going to be O of n in terms of the number of holes in memory for the worst case scenario, but it is likely to find a hole. Like if it's going to find a hole, it's likely to find one a little earlier than the other strategies will. So what about when the OS wants to find this sort of smallest hole that is large enough for that process?
Best fit.
Best fit, yeah. So best fit is if we want to find this sort of most or the least amount of leftover space. So we want to find the best hole for that process in memory. And then what about the final strategy?
Worst fit.
Worst fit.
Worst fit. So it's maybe a little counterintuitive to have a strategy called worst fit. It seems like why would you name something worst if you are ever going to use it? But the nice thing about worst fit is it reduces fragmentation because we are trying to leave the largest amount of memory possible for something else to fit into. It's not always going to be the best fit or the best case there, but this will leave at least the most space left for something else to fit into that space. It can be counterproductive though, right? Because if we sort of do worst fit, we use up, we have a 64 kilobyte space left over. Let's say we, take a, we have 64 KB left. We allocate 10 KB with worst fit. And then we have 54 kilobytes left. And then we try to map something that is 64 kilobytes. Now, all of a sudden, we've sort of run out of space because we fit something into that worst fit slot, where maybe there was another slot that we could have fit 10 kilobytes into, and now because of the fact that we use this, we can no longer fit something larger. So this is sort of the best case for fragmentation when you have like small allocations with worst fit, but not great if you're going to have like a small allocation followed by a larger allocation. Okay. Any questions on how these work in general? Okay, so let's go ahead and do this practice problem then quickly. So on the diagram below, show where a block of size 12 kilobytes will be allocated for first fit, best fit, and worst fit. We're going to assume that the blue blocks are used, they've been allocated, and the white labeled blocks are free space. So go ahead and disperse again, and let's take like 2 minutes. If you want to disperse, chat about it, do the practice problem, and then come back to the general channel in 2 minutes.
Dr. Delosier,
Yeah.
is the example labeled like lowest address at the bottom or lowest address at the top?
Oh, it's labeled lowest address at the top.
Yep, thank you.
Mm-hmm.
Back.
Okay, so I should have put this detail out first. Sorry. So the low address is at the top. Highest address is at the bottom. So where is first fit going to go? Let's go with back row. Tell me where first fit goes.
The 32.
32. Yeah.
Oh yeah.
No, definitely.
So that's first fit because we go through and find the first thing in memory. What about best fit? Middle row. Where's best fit go?
16.
16.
Yep.
Right.
Yep.
So that's best fit because we are trying to leave the least amount of space left. And then front row, where is worst fit going?
To the 64 KB part.
Yeah. Nice. Okay, so best fit goes here, or sorry, worst fit goes here, because we're trying to leave the most space available left. So that leaves us with 52 kilobytes left over there. So nice, good work. Let me make that a little bit larger again. Okay, so hopefully that gives a decent idea of how this works. That we have this sort of low address. The first fit finds the first block available. Worst fit finds the one that leaves the most space. Best fit finds the one that leaves the least space. Any questions on that? Are we good? Okay. So let's move on. So fragmentation, as we sort of discussed already, can occur with the first fit and best fit strategies, meaning that the free space ends up getting broken into small pieces as processes are created and complete their execution. So there are two types of fragmentation that we're going to talk about. The first one of these is external fragmentation. So external fragmentation occurs when there's enough total memory to fit a new process, but the individual holes are too small to fit that process. So if we look at the diagram above, if we had something come along that was 80 kilobytes, we would be able to fit 80 kilobytes into the total available space here. We have 128 kilobytes here, I think, or a little less than that, 112. So we have space available, but we don't have it in a contiguous block. And so this is what we call external fragmentation, that we've sort of outside of the processes that have been allocated already, so external to the processes that have already had memory allocated to them, we don't have enough space, or the space is fragmented too much to allow us to fit a new process in. Need the term here. So the 50% rule here shows that with first fit, given n blocks allocated, another half times n of those blocks will be lost due to fragmentation, meaning that with first fit, eventually roughly 1/3 of memory will be unusable due to external fragmentation. So this can get pretty severe at times because of the fact that we are sort of continually breaking up memory into smaller and smaller pieces. Okay. We can also have internal fragmentation. So internal fragmentation occurs if we allocate fixed size blocks of memory. So instead of allocating sort of completely variable sized blocks, we may want to allocate slightly smaller blocks of memory. So, for example, a process might want 65,000 bytes of memory. That's not a power of 2. So generally speaking, most of the stuff we have on computers works in powers of 2. And so we may want to have a particular allocation size that matches that allocation scheme. So the fact that we want most of these things to be powers of 2 means that we may specifically have blocks that are at powers of 2. Oh, is everyone else able to hear still?
Yeah, I can hear.
Okay, cool.
Get over here.
Okay, so just Austin, hopefully. Hopefully that fixes itself. So here we have, essentially that we may want to allocate fixed size blocks of some power of 2 size, so that we don't sort of end up with very strange sized blocks in memory, right? It's likely that we'll have more external fragmentation if we don't allocate in sort of normal sized blocks. If we allow people to sort of use these odd sized byte allocations and things like that, we're going to lose things here and there a lot more often. So generally speaking, we're going to allocate things in, eventually a page size, but in some fixed size of memory. So we're going to have, something like a 65 or 64 kilobyte allocation rather than a 65,000 byte allocation. And because of the fact that the process is not actually using all of that memory, we do have some internal fragmentation as well with this type of a system where we allocate more space than the process actually needs to use. So one of the ways we can address external fragmentation is compaction. That's what we talked about a little bit earlier, where we sort of move things around and put them into one space in memory instead. So we talked about address binding a little bit, which is that, when we write our code, we compile it down, we assign these locations to variables, we assign locations to functions, we bind addresses based on what things we're actually using in our code. When we move things around in memory, those might change. So go ahead and chat a little bit about this. So how does address binding how is address binding affected by compaction? So scatter. Okay, what do we got front row?
We were talking about, so yesterday we talked about how you want to statically define like the memory bounds during like compile time.
Mm-hmm.
But if you're shifting your memory around to kind of keep all your memory blocked together, that's going to happen dynamically during runtime.
Right. Yes, we're going to have to basically relink. We either have it be dynamic so that every time we move, we sort of have a base address that we access everything off of, like an array, or that we have to, relink everything when we move stuff. Cool.
Just, like, we can't move it.
Everyone?
If you have it if you have it binded to an address, you're not going to be able to compact it, right?
Right, so if we've linked it to a specific address, you're right, that we will not be able to move it around. So what could we do? Okay, think about it for a little bit more. I'm going to go to the back row, and then you can come back in like 30 seconds or so.
And are you saying things? Because I literally can't hear you at all.
Yeah, I'm saying stuff. Professor, can you hear me?
I can hear you.
Emily says she can't hear me. I think she just muted me, actually. Can you right-click? Can you tell her to right-click on my name? She probably muted me.
Yeah, Emily, can you right-click on his name and see if either his user volume is very low or if you've accidentally clicked mute on him?
Okay, I checked both of those. The user volume was high and mute was not clicked, but...
Okay.
Oh, wow. Interesting. That's
Very
okay.
weird.
This is fine.
Yeah. I can hear everyone else, just not Ryan.
That's odd. Okay, so what do you two have? Or what do you three have?
Well, I thought that maybe the address binding, you'd have to like compact the available memory around the address.
I couldn't hear what Ryan was saying, but I heard Josh's.
Okay, so Ryan
Input.
said we'd have to compact the memory, like we'd have to move the address bindings around, right?
That's crazy.
Yes.
Whoa, what you
Okay. Yeah, so that's a good answer. Yeah, if we compact memory now, if we've statically bound anything in that executable, we're going to have trouble moving it. We'd have to relink it to the new place in memory, which is going to be tricky.
Right.
Cool. Okay, let's head back to lecture.
How do you see they're in League of Legends? You can't.
Oh, well, like,
It says it in the corner of like the people who are online.
yeah, like it said it under his name.
Yeah, you gotta turn your game status off if you're.
Or you can keep it on. That's fine too.
I don't know how to turn it off. Like, honestly, I have it on. I don't have it on.
It is
Like,
in
I can like
settings
screen
somewhere.
share.
Yeah,
If it was
it's,
just open, it'll say that you're playing even though you're not.
Yeah.
Actually, like before, that's what it was, but I wasn't even online.
yeah. I
Is
forget.
it still saying it?
No,
Oh.
yeah, it will
No,
I think
it
say
seems
it
like
the text even like
Okay.
the
even if the client's
app
up,
is
like it'll like hold on.
Yeah.
If I just opened the Minecraft client.
Because if I was playing, I couldn't like continuously play because I turned off the I turned it all off, so it's all right.
We're not judging you that much. Okay.
I am. Thought it was hilarious.
So we got a couple good answers here. I think the main thing everyone talked about was that if we have things statically bound to an address, it's going to be hard to move those addresses if we compact. So moving a process that has been statically bound will be difficult. We could go with something. One of the groups said we could have something where we have a dynamic, linking process. So if we have basically, we could access everything off of the base address of this executable, right? Essentially, like the entire process is a big array of bytes, and just say, okay, I'm accessing byte number, 15 from the base of this, or accessing byte number 1024 from the base of this, and we could, we could dynamically address bind, but it would be slow. So there are a couple options here. The second one's not a great option there. We don't really want to. Sorry, I'm going to go live again, by the way. I forgot to re-hit that. So it would be slow to be able to move the process or to do the dynamic linking. Moving the process might also be slow and difficult. We haven't really talked about this much yet, but it's very difficult at runtime in a C application to identify where pointers are. So if we're just looking at memory and trying to figure out, like, if we're trying to move a process, for example, we'd have to, know where all the pointers are internal to that process, basically. So we'd have to be able to remove those pointers, point them to the new place in memory, change where they point to be correct in this new location in memory. And that's very difficult to identify what a pointer is. Mostly because of the fact that, like, if we know the IEEE floating point representation, if we look at even just like single precision, we have this setup where we have like the sine, exponent, and mantissa for floating point numbers in memory. So because of the way that these are structured, having any sort of floating point numbers in memory can make it look like you have addresses in memory. And it's pretty easy for a floating point number to just happen to conflict with an address or look like an address, and then you can't move things in memory without knowing whether or not this is a floating point number or an address. If you move it and it's a floating point number, now you've just created some random float value in the program. If it's not an address, if it is an address, you have to be able to move it. So this sort of binds you a little bit in terms of what you can do with address binding, because you have this memory that looks like addresses. So you can't figure this out. In more in more modern languages like Java, a lot of these other languages, you have this map that tells you where addresses are in memory, and so it's a little easier to do this. But like with straight C code, you don't know which things are addresses and which things are floating point values, because it costs something in order to mark it, whether this is an address or whether this is a floating point value. So we don't actually keep track of that. Okay. So that is contiguous memory allocation. We're just going to do a quick check-in here. Not too difficult, just sort of a quick review and an easy way for me to keep attendance. So go ahead and log into the Kahoot that should be showing up in a second here. I'll put the pin in chat just in case. Missing one. Who are we missing here?
Emily can't see the live stream, so I sent her the code.
Oh, okay. Okay. Okay, cool. Emily, I will try to read these out loud for you and give the answers. So I think the answers for all of them are going to be the one on the top left is first fit, and then the one next to that on the right is best fit. The one below that is worst fit. So I think that's the answers for all three. So, okay, 3 questions. Which allocation scheme has the fastest run time? Red is first fit, blue is best fit, yellow is worst fit. Okay, yeah, so first fit is the fastest because that just has to look through the queue, find something that is the correct size. It doesn't have to look through all of them. So best fit and worst fit are always going to be O of N because they always have to look at the full queue unless we get very lucky and find like an exact sized hole for best fit. It is possible that we find something like that, I guess, in best fit. But for the most part, these are going to be O of N for best fit and worst fit. In every case, first fit will sometimes be a little faster. Lizard King was fastest. Next up, which allocation scheme leaves behind the most remaining space? Nice, yeah, so worst fit is the most remaining space left over because we're trying to find the hole with the most remaining space there, the worst fit for that block. Stewie was a little faster that time. Okay, and finally, which allocation scheme leaves the least remaining space behind? Good, nice. So best fit. So we get the fastest quick draw in the class here. So we got C Pancake. Nice work. Lizard King in second. I guess Stewie edged him out with the quick Kahoot skills. Runners up Peanut Butter and Mr. Mondel. So nice work. Just a quick check-in and mostly for me to take attendance here. So, okay. So great work on that. Those are great answers. Hopefully we remember those come the exam time. So we're going to move on then to paging. And so paging is sort of the answer to why we don't use contiguous memory allocation for processes anymore. And this is getting into why we use virtual memory. So there's another chapter on virtual memory and how that works. But this is sort of getting into the meat of what virtual memory is on a system today. So paging breaks the physical memory into fixed size blocks. What do we call them in physical memory? Anyone remember?
It was frames.
Frames, yeah, nice. And then in the virtual side of things, we're going to call them pages. So this is not too complicated. Just we have frames in the physical memory. Those are matched to pages in virtual memory or in logical memory. So what the application programmer sees is a page of memory. What the hardware sees is a frame in physical memory. So when a process is scheduled, its pages are loaded into the available frames. And under paging, we sort of divide the address into two different parts, the page number and the page offset. So this allows us to basically, characterize the address as a page number, which is the page location in memory, and then the page offset, which is for how large that page is. We're just saying, like, which byte of the page do we want from that page. So that's really the whole concept here, is that now we're going to have these fixed size blocks of memory that we're going to allocate to processes all over the place. So now we're not going to have this setup where we have a continuous block of memory and the process is allocated into there. We're going to have a bunch of different pages interleaved in memory that different processes are allocated to. So the page number is used for a couple things. It's used first to index into a per process page table. So this page table contains the base address of every frame in physical memory, and the offset is the location of the frame, location in the frame being referenced. Essentially we're just looking at where is this frame going. This allows us to sort of translate from a virtual to physical address without changing at least part of the address. So to translate, we take the page number, we look that up in a table, we find the frame number, and we just essentially do this substitution here that you can see, that is substituting the frame number for the page number, and then the page offset stays the same in both of these. So we essentially just replace the page number with the frame number. That gives us the translation from virtual to physical memory. So now the OS can decide what the frame number is for every page number per process. So we have basically this, we have a pair, we have a page number, comma, PID maps to a frame number. So that's what I mean by this. This sort of syntax here is that we have this pair of things, the page number and the PID, and that maps to a frame number. So we might actually have the same page number for multiple processes. So we could have, page number 0, process ID 512, maps to frame number 1, and we could have page number 0 in process 2142 map to frame number 2. So they could access the same exact address, the same exact page number and page offset from both of these processes, and end up with a different location in physical memory when the hardware actually loads or stores to that address. Okay. Are we understanding this concept so far? Okay. If I'm not hearing any questions, we're gonna continue on. Hopefully it's okay. So we determine the number of bits used in the page offset and in the page number / frame number by the size of the pages that will be used in the hardware. So because we're taking an address and we're dividing it up into these two things, the number of things in the offset or the size of the page will determine how big both of these are. So usually we don't determine this based off of the page number. We decide how big our pages should be, and then we deal with the ramifications there. So for example, if we have 4 kilobyte pages, that means we have 4,096 bytes per page. We need to be able to index each of those bytes. And because we need to index each of those bytes, we have, 2 bits or 2 options per bit, right? So if we take the log 2 of the size of our page, that'll give us the number of bits that we need. So, this is the inverse of if we have 2 to the 12, means that we can represent 4,096 different values. Should use equals arrow there. So we have, that implies 4,096 different values because of the fact that we have 12 bits to use, and each of those bits has 2 different values. So that determines the size of our pages. I have a couple practice problems here. So we're looking at, first, in a 32-bit system, how many bits are we going to use to represent the page number if the page size is 1 megabyte? How many unique pages are available in that system? And then finally, how many page table entries would be required for a 64-bit system that uses 4 kilobyte pages? So I'm going to give you maybe 5 minutes to do this, and then we'll sort of sum up for the last 3 minutes. So go ahead and scatter, work on these in your groups, and then I'll come around and check on you. Can you hear me, Austin? Oops. Oops, I just, sorry, I just disconnected. Oh, okay.
Yeah, I don't either.
Okay, how are we doing?
We're pretty
2.9.
confused.
What was that?
2.9.
2.9.
Ryan, I don't remember you
Emily-
saying that.
Emily,
that
I don't
number
remember.
one time.
Emily said to take the
Definitely
lot
confused.
2 of 8 million because there are 8 million bits in the
Okay, so for the first one here, we have a 1 megabyte page size. So how many bytes is 1 megabyte total?
How many bytes?
How many bits do you need to represent 1
bits?
megabyte?
There's 4 bits in a byte. That's all you need to know.
No. Is it not 8 million?
It's not 8 million, no.
Okay, well there are 8 bits in a byte, so
I guess how many bytes are in 1 megabyte? Yeah, so you are right on the number of bits that are in 1 megabyte, but we need to know how many bytes because we're not addressing each bit.
1,000.
Yeah,
A million.
Yeah, so it should
1,000?
be like a million some, right?
Oh yeah, a million.
So that's 2 to the what, I guess.
A million is 2 to.
2 to the
Log
10.
base.
I don't know. Yeah,
I'm honestly like a genius.
Josh, you got it.
I don't know how to use this calculator.
I'll use it. What do you need to know?
Do log base 2 of a million.
I don't even know what that means. You
Give
expect
it
it
to me. Give it to
hard
me.
to know what that.
Oh, I got it. Just Google it. 19.9.
Yeah, so it's close to 20 in this case. So it's like 2 to the 20th would be 1,048,576. 48,576. So that it's 20 bits basically that we would use to represent the page. Or that would be how many bits we would need for the actual page offset, right? So then the 32 minus that is how many we would use for the page number.
Okay.
Okay. And then I'll let you continue on from there. I'm going to check on the other groups real quick. How are we doing here?
Stuck.
I think we're just a little confused about how to what like the 32 byte or bit and 64 bit. Because like in the example, it's just like you just do the log of 2 of like the size of the pages. So that's what we did.
So the page number plus the bits for the page number plus the bits for the page offset should be equal to the total number of bits in an address. So if we have 32, for the first example there, if we have 12 bits for the page offset and we have 32-bit addresses, then we're going to have 20 bits left for the page number.
Okay.
So then here we should have a different number for the page number and the page offset, but it should be similar. So give you a couple more minutes to think about it, and then we'll come back to the lecture. So
Pages.
okay.
Is that a misnomer? Because the bytes would coordinate to like physical memory. So wouldn't those be frames, like 4 kilobyte frames, or?
Well, pages and frames are just virtual versus physical.
Right. But there are more frames than there are pages, right?
No.
No.
The same? So then how can you have the same page mapping to different PIDs?
So you should have you should have different pages mapping to the same frame, possibly. They might not be all in memory at the same time, but we have less frames than we have pages, basically, because we might have some processes that are not in memory at a certain time.
Oh, okay.
Yeah. So the frames are like the actual physical memory. Those are fixed, guaranteed to be the same amount every time.
Right.
So yeah. So when I say unique pages available, I mean like in terms of like I do actually probably mean unique frames available there. Is probably a better way to put it. Because we are looking for like how many are we limited to, given the bit size of the system.
Right.
And 32
So we got
bits.
2096. The second question.
Okay. $2096. Where'd you get 2096?
There's 40.
4096?
Okay, 4096 is right. Yeah.
4096. Sorry.
Okay, cool. Okay, I'm gonna move us all back to lecture so we can finish up. But sounds like you guys have a handle on it. Okay. I'm gonna move everyone back. So.
It's to the 20th gets a million, right?
So the offset
So would you
is
subtract
20 bits, and then 30 minus the offset gives you the
Yes.
number of bits. Yeah. So the answer is 12.
Yes.
Okay.
Cool.
Got it. We're good.
Oh, Emily, that's what I said.
So the first one, we have 1 megabyte. I'm going to just summarize real quick and then let you go. So we have 1 megabyte for the first thing here. And that means we have roughly like a little over a million or 2 to the 20th in bits or bytes in each page, which means we have 20 bits for the page size, or for the page itself, the page offset. And that leaves us with 12 bits left for the page number. So then how many unique frames do we have in that system?
2 to the 12th.
Yeah, 2 to the 12th. About 496 frames, because we're just basically saying, given the number of pages or frames that we can represent, that's how many we have left we could have, if we added the PID in, we have, that times the number of PIDs for the unique pages in the system. But in terms of like what each process sees, they're only going to see that 2 to the 12th. So then for this last one, if we have a 64 kilobyte system that uses 4 kilobyte pages, let's edit this. So 4 kilobyte pages we talked about is 12 bits, right?
Mm-hmm.
And in a 64-bit system, we're going to have 52 bits left for the page number, right?
Yep.
And that's going to leave us with, same calculation, 2 to the 52 equals a lot.
And 5 to the 15. Times 10 to 15.
Yeah, it's like, I mean, it's whatever that, it's not a tera even, it's peta.
Too many.
It's bigger than peta. It's like 1 exabyte.
Yeah, is it exabyte?
Exabyte.
Yeah, so it's a lot of pages, right? So this is way too many to keep track of. And we'll talk about some of the issues with this. Even if we go to 48 as like the more reasonable setup for what our systems have today, that still leaves us with 48 minus 12 is 36 bits, still like trillions of pages to keep track of. So that makes our page table that we're looking up these page to frame number mappings in huge. And we'll talk about that in next class about how we handle some of that complexity. So, or maybe Friday we'll talk about that. So thanks everyone. Hopefully this wasn't too tech issue difficult. I'm still debating whether I want to just switch over to Hangouts, but I do kind of like the ability to throw you into separate discussions. I don't know if Hangouts has that or not. I'll look into it, but otherwise I think we're done for today. So I will see you on Wednesday.
Thank you, sir.
Cool.
Yep.
Sounds good. Thank you.
I'll see you guys later.
Stuff.